Howdy, I'm Armando Zavala. I'm project manager of AutoBots, and this is our autonomous vehicle development platform. Our presentation overview, we're going to start off with the introduction and the background, problem statement, concept of operation, functional requirements, conceptual block diagram, as well as the functional block diagram, performance specification, responsibilities and schedules, significant assumptions, project impact, technical merit, conclusion, and questions. And this is our engineering development team. I am the project manager. Sukith is our integration engineer. Dakota is our hardware and system engineer, as well as Nick. We also have Spandan as the software engineer. And then our stakeholders is Dr. Langari. He's our advisor and sponsor. Our objective for this project is to create an open architecture that could be augmented with additional software and hardware capabilities designed to be used and branch off to future projects for autonomous vehicles. It's meant to be a plug and play type deal to save money, eliminate the need to purchase a new vehicle with this functionality. Also to have a fail-safe system to make it more safe, and to significantly increase the runtime compared to drones when using research. A little bit about the background is that self-driving hardware and software ranges from $70,000 to $150,000. And also the market value is projected to increase by 10 times by 2025. Creating a new platform from scratch takes years and at times is very inefficient. Pre-made autonomous vehicle kits also cost around $30,000. And as far as our need goes, Dr. Langari had proposed an interest in having an overall autonomous vehicle system which is easily adaptable for projects of all kind without requiring major redesigns. One project use he would like to do is create a 3D map of rural areas without having to put researchers at risk when the conditions aren't too great. And like I mentioned before, it would have a longer runtime compared to drones. This project would need a variety of equipment such as sensors and cameras, and our project would essentially give it support for new algorithms and accommodate new equipment. Our problem statement, autonomous vehicles and software right now is very complex and expensive. Consumers should have a cheaper method of getting autonomous vehicles, as well as automotive kits are not very open sourced and very private. Developers should not have to spend time handling lower level AV, programming to gain data, and it should have a wider compatibility. Our solution is to create an open source autonomous vehicle development program covering the basics of autonomous vehicle software that empowers users to build on top of the program. We would provide a general starting point covering sensing, actuation, and AV algorithms, as well as the plug and play capabilities, and contain multiple fail-safe systems. Our deliverables is to provide a baseline autonomous software package consisting of our one LiDAR sensor, an INS system, central computer, 2 cameras, and a PCB connecting to the existing actuation system. Level 3 autonomy support, which will include environmental detection, an emergency fail-safe system, and allow users to add new algorithms and sensors as they please. Here we have deliverables broken up in 3 parts. We have the sensing to have our sensor mounting, quick and organized data. Processing would be our 3D mapping of the LiDAR and INS, object detection, AV algorithm, and our actuation would contain our PCB mounting, the fail-safe system, and it would control the brakes, acceleration, e-brake, and steering. And then the concept of operation, we will be using a Ford F-150 as our test vehicle. The vehicle would contain an onboard processing unit equipped to receive and organize the data from our sensors, camera, and the INS. And as well as the PCB will then be able to take this translated data from the computer and run tasks on the actuation system, as well as contain the fail-safe system.
Okay, I'm gonna be speaking on the functional requirements. We have 4 main subsections. It all begins with the data acquisition. This is where our sensors and actuators are gonna be. The main goal for our data acquisition is synchronizing all the data that comes from the sensor and actuator, and that way our system acts as a whole. And we also need it to be scalable. That way we can adjust the size and feed the main processing however we need it to. We also have the main unit. This is where our data collection, data processing, and data communication will be. And that goes on to the PCB. These are some of the features we have for it. It's going to have 5 volts for the microcontroller, 12 volts for the motor driver. Its output is going to be the analog signals that are going to be between 0 to 5 volts. And it also has to be able to read analog signals between 0 to 5 volts. From there, we have our power management. We're going to use standard power outlets for the sensors and other hardware. And this is going to be sourced from the vehicle that's going to be converted to the respective voltages. This is our basic conceptual block diagram, basically summarizing what I just said. We have our sensors, LiDAR, cameras, all going into the processing unit where we have the data acquisition. Like I said, from there it goes into the PCB where it can communicate with the parent computer. And then we have our power management, which is the Ford. This is our functional block diagram. We have it started. We're still pending on our PCB boards. So what we have right now, we have used from Mava Innovations until we get ours approved. But this is the main concept of how it should work. It has our voltages, data passages, and that's pretty much it. These are some specs on our LiDAR sensor. It's going to be a Velodyne VLP16 LiDAR. Has the range 100 meters, rotation rate 5 to 20 hertz, power 80 watts at 9 to 18 volts DC. Has a 300K to 600 points per second speed and up to 1 megabyte per second via Ethernet. And these are some of the performance specifications that we have. We have 3 main keys that we want to try to reach. The first being responsiveness. We've designed everything to be accurate, to have accurate reactions and proper decisions. This will all be based on the decision-making algorithm, which is made to emulate the average human's response of 250 milliseconds. That's from sensing to actuating. Next, we want to focus on the resolution. We need high resolution in order to feed the DMA and allow it to provide high speed and accurate data collection at practical speeds. For now, what we have planned is to get approximately up to 30 miles per hour with everything functioning together and accurately. And last is safety. All the efforts of providing accuracy, precision, and correctness are with the dedication to providing a safe product as a priority. I guess this is the hardware as well. This is our camera. It's just the F-Flower Black Fly SPOE camera. Its resolution is just 2048 times 1536 pixels at 35 frames per second, 10 to 100 megabytes per second with Ethernet. This is our processing unit. It's a Cyprin Trio. Has the IMU data of 200 hertz with latency under 200 milliseconds. Has GPS up to 100 megabytes per second with Ethernet. It's IP68 rated, and its accuracy is listed right there. This is our processing unit. It's a Nuvo. It's one of the more updated ones. It's an Intel i7. Has the NVIDIA GTX with 512 gigabytes SSD. And it's also very heavy duty, which is what we're aiming for since we're going to be putting this on a Ford. This is our vehicle. Support F-150. The software we're going to be using is the AutoWare AI. This is what Mava started with. So we're going to continue to work with that and just makes some of the sensor drivers already programmed with this software. So that's what we're going to continue to improve. We're also going to be using ROS, which is just our robot operating system. This is good for the collection of open source robotic software frameworks. We need to remove the stopping system for various changes on the fly editing and testing. And it also runs on Linux.
I will be talking about the responsibilities of each of the team members of our project. So this is the assignment matrix for the research section of our project. So Armando is our project manager, and he will be reviewing most of the stuff. So he will be having the letter R, which in the legend shows us that R refers to reviews the task. So in the research section, for the sensors part, Armando will be reviewing it. Sakit and I will be giving input, and Nicholas and Dakota will be secondary, as they will be working with partners to finish the research for sensors. For the actuator control unit, Armando, the project manager, will review it, and Sakit, Nicholas, and Dakota, the hardware engineers and system integration engineers, they will be doing most of the work for the research of the actuator control unit. And for that, there will be secondary, which means they will be performing with partners, and I will be providing input. For the AutoWare, which is sensor support, algorithms, NDT matching, sensor fusion, and algorithm design, Armando will review it. Sakit, Nicholas, and Dakota will be giving input, and as I am the software engineer, I will be doing most of the work, so I'm primary. For the PCB programming, me and Armando will be working on it. We'll be working on most of it. That's why both of us are secondary, and the rest of them will be providing just input. For the system integration part, this is mostly Saket's responsibility. So he's going to have a lot of P's in this part of the assignment matrix. So for the GPS implementation, Saket is the primary. Armando will be reviewing it, and the rest of us will be giving input. For the IMU implementation, it's the same as the GPS implementation. For the data processing and management, Armando will be reviewing it. Saket, Nicholas, and Dakota will be working on most of it. That's why they're secondary, and I will just be providing input. For the integration of camera, Armando will be reviewing it. Me and Saket will be giving input, and Nicholas and Dakota will be working on most of it. For the sonar, radar, and LiDAR implementation, it's the same as the integration of camera, where Armando will be reviewing it, Saket and I will give input, and Dakota and Nicholas will be secondary, and they will work on most of it. For power management, Armando will be working on most of it. That's why he's primary for this one, and the rest of us will be giving input to him. For the AutoWare data and algorithm, Armando will review it. Saket, Nick, and Dakota will be giving input, and I will be the primary worker for this, for the AutoWare data and algorithm part of the system integration. For the PCB and sensor communication, me and Armando will be working on most of it, and the rest of them will be giving input. For the PCB and actuator communication, it's the same as the PCB and sensor communication. Armando and I will be working on most of it. The rest will give input. The next section on the assignment matrix is the testing part. For that, for the algorithm testing, for the testing section, Armando and I will be working on most of it, as I am the software engineer and Armando is like the secondary software engineer. That's why we will be working on most of it. For the algorithm testing, for the data processing testing, for the PCB testing, and for the power testing, Armando and I will be working on most of it, and the rest will give us input. Now we move on to the documentation part, where everything's going to be split equally amongst all of us. So for the modular sensor and documentation, but for everything, Armando will be reviewing it as he is a project manager. So for the modular and sensor documentation, Saket, as a system integration engineer, will have the primary job to finish the documentation for this. For the data collection, it's going to be Armando with the primary job. For algorithm testing methods documentation, it's going to be me with the primary responsibility to finish that. And for vehicle-related documentation, Nicholas and Dakota will be working on that together, and the rest of us are going to review it or provide input. For the CDR presentation, for the final presentation, everyone will be putting in the same amount of work. So that's why it's secondary for everyone, as we're all going to be performing it with each other. For the final demo, it's the same. And for the sign off by professor, advisor, and sponsor, everything's the same. Everyone's going to be performing. This is the Gantt chart overview, and this is used for scheduling of the individual tasks of each of our projects. This Gantt chart includes all the tasks that we will be performing and their time length for the spring semester and the fall semester. Now moving on to the spring semester, we got the overall system document review, the AutoWare software research review, the parts testing, the PCB research, the actuator control unit redesign, the SDP. So basically this spring semester, you will take up most of our time just designing the PCB, getting that done with. And so that is going to be from March 2nd to up until the next semester starts, which is like the fall semester in August, like mid-August area region. So this is where we have like the begin date for each task and then the end date. So yeah, we gave about 2 to 3 weeks for each task to get it done with. So yeah. Now moving on to the fall semester for the Gantt chart. This is where we get most of our system integration, or like all of our system integration done. So putting all of our hardware together, the Ford F-150, the cameras, the LiDAR, the sensor, the actuators, everything together. And this will begin from whenever fall semester starts, which is in August 16th. So after we're done with developing the PCB and designing it, we're going to be moving on to the integration part. So we're going to have PCB development integration, sensor integration, autonomous software integration, documentation development, CDR, the actuation, the PCB testing, power and data input, position testing, sensor testing, autonomous software testing, and then final documentations and reports and presentations and stuff. So everything should be done by November 26th, 2021.
Next is our work breakdown structure. We took all the tasks that were mentioned in the Gantt chart and broke them into categories, and then those categories are somewhat broken into the orders in which the task must be complete. There's more detail about this in previous slides with the network diagram. Here's the main network diagram that includes both spring and fall. Move on. For our spring network diagram, this is our entire planning phase of the project. Before this, we need to complete all research, part testing, and future scheduling. Tasks 1 through 3 are mainly hardware research that needs to be complete before we begin testing parts and the processing unit in task 6. This research includes the overall system documentation, previous processing unit documentation, and sensor documentation. We gave allotted 2 weeks for all research and 3 for all the initial technical actions, such as part testing. Tasks 4 and 5 are the research needed for the PCB and software. Each of these tasks is followed by tasks 7 and 8 respectively. These tasks are first development of the PCB integration and redesigning the previous group's actuation control unit. Again, we allotted 2 weeks for all research and 3 for all initial technical actions. After all 8 previous tasks have been completed, we'll begin working on the SDP in task 9. We gave 1 week for this task because we believe all group members should be putting effort into it. In task 10, we decided that is the summer and we will use this time to either catch up or get ahead. We're going to save this time to be determined based on what we need at that time. Next is our entire fall network. This is where all execution and the entire systems testing is done. Following summer, the initial tasks are 11 through 13. Task 11 is a long 6-week task for mainly the project manager, where they will gather and organize all documentation needed for future reports and presentations. The others will work on testing the PCB and the actuator, as well as integrating the autonomous software. Following tasks 12 and 13, we'll begin work on the power and input data in task 15. And again, all other tasks other than the documentation development were allotted 3 hours, or 3 weeks. Task 14 is a prerequisite task for the task 16 and 17. Task 14 is a sensor integration, which must be done before we begin position testing and sensor testing. And again, we gave all these tasks 3 weeks. Once all tasks prior to the CDR and task 18 are complete, we gave it 2 weeks to complete such CDR. Following this, we gave another 3 weeks for all autonomous software testing, and this is the fully integrated system. This is a time where we should kind of have all hands on deck. So we should really have a whole lot of people working together. So 3 weeks should be enough. And then our final 2 weeks will be preparing for final documentation and the final presentation.
So our list of assumptions are, we're assuming that all weather conditions are going to be ideal for testing. And we're also assuming that there's a practical learning curve and a time period for learning the new softwares that we're working with. Additionally, we're also assuming that we'll have continued access to all labs and testing equipment and just generally the resources that we've been provided. And lastly, we're assuming that there are no general mechanical faults in the vehicle that's kind of beyond our control. For example, like the oiling system, cooling systems, radiators, fans, belts, transmission, suspension components, steering components, the braking system, and the exhaust components. And the potential limitations of our project are specifically what we use from the assumptions. So obviously having non-ideal weather conditions is going to impact some of our outside hardware and system testing, and especially when it comes to integration. And additionally, the COVID-19 health restrictions. We also will be limited if we do have a larger than expected learning curve of implementing or troubleshooting the new software, such as AutoWare, CUDA, and the robot operating system. And lastly, another limitation is the lack of functionality and activities within the existing AutoWare functions themselves. So for example, if this happens, we would have to resort to other softwares in order to complete the same functions through AutoWare. So the impact of our project and basically the merit of it is that this is a more practical alternative to a drone. And pretty much this is a cheaper, better placed alternative, such as a plug and play versus generally buying a car that has an autonomous ready integration. So all autonomous vehicles now, like Armando said earlier, have a certain price point, and we aim to undercut this price point by significant amounts. So not only would it help be a lot more attainable, it'll be like a lot more accessible to the public. Lastly, this also provides a safer driving and data collection environment, along with opening the door to other autonomous AIs in consumer vehicles and in public transportation. So in conclusion, the AutoBots plan on developing an autonomous vehicle architecture in which we will aim to deliver an open source platform with general basics developed and a PCB successfully controlling an existing vehicle actuation system and a reliable fail-safe system, and additionally data collection from all the LiDAR, the INS, and the cameras on board the Ford F-150. Thank you. And our project specifically helps data collection, testing of autonomous driving vehicles, and ensures the safety of vehicles on the road by using additional motion sensors. And specifically, once finished, the project can be used for research purposes to help with the development of other autonomous vehicles. And our project is a good way of collecting data because autonomous vehicles have a long runtime under many weather conditions. So insofar as there are rainy conditions, and as far as there are snowy conditions, the vehicle aims to compete and basically work in all of those conditions. The only way the assumptions function into this is for us to like be hindered to work on it if there is bad weather, but the Ford F-150 should be able to operate under all weather conditions as well too. Thank you.